Modeling Friction Part 2. Let's relate pressure and surface area back to the topic of friction. I have here a spring scale, a device used for measuring forces. And if I pull from either end, that spring inside stretches, and we can read off on the scale there how many newtons of force I'm pulling with. You can see a little N for newtons. So let's use the spring scale to pull this wooden block across the tabletop and see if we can determine what the strength of friction really depends on. So I'm going to stack on top of this wooden block this piece of brass here that's 500 grams, half a kilogram, about a pound, and I want to pull it across the tabletop at a constant speed. If I do that, then I know that the force that I'm applying to pull it with must be equal and opposite to the force of friction opposing me, that friction between the underside of the block and the table surface. If those forces are equal and opposite as I pull, then the net force on the block is zero, its acceleration is zero, and it must be moving with a constant speed, and we say our block is in a state of dynamic equilibrium. And if I read off the reading on the scale as I pull, which looks to be about 1.5 newtons, then I know that I was applying a force of 1.5 newtons, which is equal to the magnitude of the force of friction. Therefore, I'm using the spring scale to measure the force of friction. It was a 1.5 Newton force of friction between the block and the tabletop. Now, Coulomb's model for dry friction suggests that the strength of friction depends on how hard this object presses into the tabletop. How can I make it press harder into the tabletop? How can I test that? Well, we can add some mass. Here's a second identical wooden block, stack it on top, replace the original brass mass, add a second piece of brass, and now I've doubled the mass of the object. Doubling the mass of the object doubles the force of gravity acting on it, also known as the weight of the object. But in order to hold up this object, our table has to now exert a greater normal force upward on it. If we've doubled the force of gravity, then we've also doubled the normal force that the table is exerting upward on the object. And that normal force, that's exactly what we mean when we talk about how hard the table is pressing on the object or how hard the object is pressing into the table. So we've increased that pressing between them that should, according to Coulomb's model of dry friction, increase the strength of the force of friction. So it should now be harder to pull this block. There should be a greater force of friction to fight me. Let's test it out. Pulling again at constant speed, reading off the value on the scale, and I see about 3 newtons this time. So in fact, by doubling the normal force, we have doubled the force of friction opposing me. But is it really the normal force that determines how strong friction is, or is it the pressure that matters here? In that demo, pressure happened to increase when we added mass. The pressure that the tabletop exerts on the block, or that the block exerts on the tabletop, the pressure between them at this surface of contact, the pressure there is equal to the normal force being exerted by the table on the block divided by the surface area of contact. That's the footprint of the underside of one of these blocks. Divided by that area, that tells us how much the pressure is. So when I doubled the mass, I doubled the normal force, but it's the same surface area of contact, I doubled the pressure. We saw then that the force of friction doubled. So what made the force of friction double? Was it doubling the normal force, or was it really doubling the pressure? Which one mattered? We can test by keeping normal force the same, use the same object, same total weight, but I'm going to change the pressure this time and see if changing the pressure between the block and the tabletop, see if that changes the force of friction between them. That's easy enough to do. Let's take the 2 blocks. Instead, put them side by side here, still linked together so I can drag the 2 of them. And now this object here has the same total mass, so same total weight. So it's the same total normal force that the table is exerting upward on the object to hold it up. So the normal force has stayed the same. But by spreading out the mass, by increasing the mass weight distribution, by doubling that surface area, now I've got this total surface area of 2 footprints in contact with the table. I've dropped the pressure that the blocks are exerting on the table and vice versa by half. This is like lying down on your belly on the ice. You're spreading out your weight, reducing that pressure. So by reducing the pressure here, has that changed the force of friction between these blocks and the tabletop? Has it increased the friction because I've got a bigger surface area? Has it decreased the friction because I've decreased the pressure? Or has it had no effect? Let's test. So if I drag once again at a constant speed and read off the scale, I see once again about 3 newtons of force. Friction was not affected by the change in the pressure. 3 newtons of force with the blocks stacked, 3 newtons of force with the blocks side by side. Friction doesn't care how you distribute the weight. Friction doesn't care what the pressure is or the surface area. All that matters is how big the normal force is. Conclusion here, it's the normal force that affects the strength of friction. Not pressure by itself, not surface area by itself, but the product of the two, the normal force, that's what determines the strength of friction. So, to recap here, under the Coulomb model for dry friction, the strength of the force of friction depends on 1, the composition and texture of the 2 surfaces in contact, and 2, the magnitude of the normal force. That's it. Changes to the pressure or to the surface area do not affect the strength of friction unless the product, P times A, results in a different normal force. So this allows us to continue to model a solid body, even something sort of complex like this combination of 2 blocks. We can continue to model that as a point mass, an object, without worrying about how large the contact area is or how the normal force is spread out over the surface. All that matters for determining the strength of friction is the total normal force, which can be treated as if it were a single force acting at a single point, the center of mass.